Welcome to the free Numpy course. Numpy is a fundamental package for scientific computing in Python. Numpy can be used for various reasons. For example, if you work with multidimensional array objects, or you want to use masked arrays or matrices. It also provides very fast operations for arrays. With Numpy you can do a lot of things like mathematical, logical, and shape manipulation. You can sort, select, and apply input and output, as well as various Fourier transformations, basic linear algebra operations, and various statistical operations like random simulation. The difference between Numpy and the Python lists is that the Numpy arrays are a lot faster and more compact than Python lists. An array consumes a lot less memory and is very convenient to use, and also has a mechanism for specifying the data types, which will lead to optimized code. So what is an array? It is the central data structure of Numpy. Essentially, it's a grid of values and contains information about the data, how to locate elements of the data, and how to interpret the elements. Please note that every element in the array needs to have the same data type. So why use Numpy? First of all, it's a fundamental library and is used by many other libraries. It has precompiled C code for basic operations, which lead to very fast speed of operation. All the elements of a Numpy array need to have the same data type, which leads to an array, which leads to less memory usage. Also, fewer lines of code will lead to less bugs. So let's start off by creating our first Numpy array. First of all, what you need to do is import Numpy as MP. In any case, if you do not have Numpy installed, you can use conda install or pip install to install the library on your local machine. If you have no fundamental knowledge of Python, you can check out my free Python course. Let's take for example that we've got the list of numbers from 1 to 6. What you can do to initialize your first array from a list is to use numpy.array and put inside the parentheses the list. So A will be initialized as a Numpy array. You can also initialize a two-dimensional array by using numpy.array and inputting a list of lists as input. If we run this code and print A and Z, we can see that our arrays will be exactly with the same elements from the lists. You can also specify the data type that you want an array to have by using the dtype equals argument. So what we do here is initialize an array of type float, so its value in the array will have a floating point. So what are some other ways for creating Numpy arrays? You can use numpy.zeros. This will create an array of zeros which have size 2, meaning 2 elements. You can also use numpy.zeros by using a tuple that specifies the dimension across each axis. So here what we do is use a tuple of 2.2. What this will do is create an array with zeros that have 2 rows and 2 columns. If you want to have ones instead of zeros, you can use the numpy.ones and specify again the shape of the array. You can also use functions like what essentially this does is that it takes the dimensions of the array you input to the function and create an array with only zeros using the same type, using the same shape. And you can have functions like ones likes, empty like, and others, not only zeros like. Also, you can initialize an empty array, which what it will do is input arbitrary values. You can also use empty-full and specify the fill value. So for example, you can specify that you want to fill your array with a value of 99. You specify the shape, the fill value, and boom, you've got an array of shape 3.3, meaning 3 rows and 3 columns, and every cell will contain the value 99. And you can also use numpy.arrange, which will create an array with values from 0 to 89. And you can also use an operation called reshape, which we will see in a future video in more detail, to reshape this array into the dimensions you want. So essentially, this array here is a one-dimensional array with 90 elements. You can call the .reshape function, turn an array. This is a case where an array with 9 values will be turned into a two-dimensional array of 3 values per row. And also a great thing about Numpy is that you can chain events. So you can specify an array using numpy.range from values 0 to 8, and you can call .shape function on it so you can see the shape. Then you can use reshape on the same array, and you can also chain even more by using reshape and then calling shape. You can use dot to do chain function calls or attribute calls. in NumPy. Today we're gonna talk about NumPy attributes. First, we can check the type of a NumPy array by using the dType attribute of the NP array. So first, we start off by defining a NumPy array that has 3 rows and 4 columns. And then we call the x.dType attribute and find that this NumPy array has integer values. Then we can specify also another array called a that has a dType of NumPy float. Let's check it out. So we can see here that the dType for the array A is float 64. We can also check the shape, meaning the dimensions of a NumPy array, by using the attribute .shape. If we call .shape for x and a, we can find that x has 3 rows, which is in the first dimension, and 4 columns, which is the second dimension. We can also find that a has only 3 elements and no second axis. The .shape attribute will return a tuple with the dimensions. We can also specifically check the dimensions of an array by using the .ndim attribute. What we can see here is that the X array has 2 dimensions, 3 rows, 4 columns, while the A matrix has only 1 dimension. Arrays with 1 dimension are usually called vectors. We can also check the size of the array by using the .size attribute. We can call x.size and a.size. x.size is equals to 12, while a.size is equals to 3. So the size operation is the product of the numbers of the .shape. It shows the sum of elements in an array. So the idea is that here we have 3 rows, 4 columns, and in total we have 3 times 4 elements, meaning 12 elements. While for the array A or the vector A, we have only 3 elements. And we can also check the item size for both arrays by using the .item size attribute. Both of these arrays have items of size 8 bytes. Why? Because both float and integer are 64 bits. I hope you enjoyed this. Don't forget to press the like button. Hello guys, welcome to another NumPy tutorial. In today's video we're gonna see all about accessing elements using row and column indexes and also using slicing operations. So the first thing we want to do is import NumPy as MP. Then we want to create a NumPy array. We want it to be a 2-dimensional array which will contain 2 rows of 3 elements. So let's initialize it. If we want to check, in order to access an element of this NumPy array, we can use brackets. In this case, the first element of the brackets will be the row number and the second element will be the column number. So here what we ask Python to do is access the first row and the second column of the first row. So the result here will be the value of 2 because the first row is this one and the second column is this one. Again, remember that indexing in Python and usually in programming starts from 0. So the first element will be accessed by using the 0 value. Okay, so let's also visualize Z, and moving on, let's talk about a little bit about slicing. By using this notation, what you do is ask NumPy in Python to return all of the columns. By using this notation, you ask NumPy in Python to return all the values of the specific dimension. So in this case, what we ask is that we want the first row and all of the values in the columns for the first row. So what we get here is a specific row. If we run this code, we will see that the values will be 1.2.3 and all of these will be inside an array. If we want to get a specific column, what we do is ask NumPy to give us all row values for a specific column. Let's run this code. As we can see here, the first column, which we access by using the 0 value, is 1 and 4. Absolutely amazing. And you can also use this kind of operations to access multiple rows and columns. Here what we do is ask NumPy to return the first and the second row and the first 3 columns for each of these 2 rows. Wait, what happened? I just did a mistake. What is my mistake? Very simple. Here, this notation goes from 0 to 0 because this operation accesses the values from 0 to 1, but 1 is not included. So if we wanted to access the first 2 rows, what we needed to do is do 0 notation 2. Same mistake here again. We access 0.1, but we do not access the third column. If we want to access the third column, what we do here is 0 to 3. So here, what essentially happens is that we return the original array. But bear in mind that here, what you do is return a view of the array. So if I set this equals to A and I go and change the value of 0.0 equals to 99, you need to be very careful because the value of Z will also change. Check this out. I actually changed the Z array by using the array A, which contains the view, or let's say the reference, or the memory direction of Z. So you need to be very careful with such operations using NumPy arrays. Also, it's very important to understand that you can use this kind of operations to change elements inside of an array. So you can actually access the element in the position row 1 column 2, so this is the value of 2, and we can change this equals to 100. If we print this out, 2 became 100, and you can check it out by printing out all of the array. So yes, we have 100 here, and you can also use this notation to change multiple rows at a time or multiple columns at a time. So here we specify that for the first column we want to change all the values of the rows equals 10. So think what this will mean. So think what the result will be. Let me spoil it for you. The value 99 and the value of 4 will become equal to 10. Let's check it out. Absolutely amazing. We have 10 and 10 here. And now you are fully equipped to use slicing and indexes and work with NumPy arrays. In today's tutorial, I will teach you how you can convert a 1D NumPy array to a 2-dimensional NumPy array. First of all, we want to import NumPy as MP. After that, we want to create a 1-dimensional array using a list for initialization. So specify array A to be a 1-dimensional array with elements 1 to 6. We can also check the shape of the array by using the .shape attribute of array A. As we can see, the result is that we have 6 elements and only 1 dimension. A very simple way to add a new dimension is to use numpy.newAxis operation. What this does is that adds a new axis. So let's check it out. We will create A2 and we can see that the new axis is added as a row. We can also visualize A2 very easily. And we can see here that the previous array is turned into a vector of another array. Let's check it out. Specifically, when we use numpy.newAxis as the first element of a new array, what we do is that we ask for the previous vector to become a row vector, meaning that the previous vector will be just the new row of the new array. We can also add dimensions in terms of columns. For example, if we use numpy.newAxis as in the second position, what we essentially do is that we turn A into a column vector. So previous array, the 1-dimensional array, will be just column of the new 2-dimensional array called vector. Let's check it out. So here we see that we have 6 rows and 1 column, because our row before was like 6 elements long, so these 6 elements are used as columns right now. We can also use the numpy.expand dimension. What you do here is give as argument the 1-dimensional array and also the axis parameter. The axis is used to control whether this could be a row vector or a column vector. For axis equals to 1, what we see here is that it is a column vector. So these two operations are pretty much identical. We can also use numpy.expand dimensions with axis equals to 0. What this will do is that it will turn A into a row vector in the array C. So if we check out the shape of C, it will be 1 row and 6 columns. It will be 1 row with 6 column values. So this is how you can actually convert a 1-dimensional to a 2-dimensional array. And by using the .shape operation, you can check the result of your conversion. numpy.newAxis and numpy.expand dimensions are the two things that you need to know in order to do this operation. Hi, in this tutorial we're gonna see how we can combine arrays and, creating arrays from existing arrays, using stacking and concatenation, and actually learning how to split an array into equal sized arrays. So the first thing you want to be doing is importing NumPy as MP and creating 2 arrays. I'm gonna do a very simple example here, and I'm gonna be specifying A1 and A2. So let's say that we want to stack these 2 arrays vertically. So we can use numpy.vstack and let's see the result. What you do is actually put the one array below the other. And the result would be A1 being on top and A2 being on the bottom. Then we can do a horizontal stacking, meaning adding one array and another array column by column. So what you can see here is concatenating A2 into A1 and returning a new NumPy array. Here we have A1 having the first 2 columns and then having A2 with its own columns appended into the returning array. Then we have the .reshape operation, so you can check out, for example, X here. So this is a vector that we are going to be creating for the next example. And let's say that we want to split X into 3 equal arrays. We can use hSplit, specify the matrix that we want to be splitting and how many parts we want this array to become. So the result will be this array split it into 3 distinct matrices. So what we can see here, it's really interesting actually, is that we have each of the rows split into 3 pieces. And the result would be 3 arrays with each split of each row inside of it. You can also do a vertical split, so you can split X vertically into 2 distinct arrays. So what it's gonna do is take the first row and the second row, split them apart into 2 distinct arrays. Finally, you can use concatenation of arrays by using numpy.concatenate. Let's check it out. So here, by using the simple concatenation, what you do is actually take array B and append it on the back of A. And you can see that you finally result into a new array that has all the elements inside of it. You can also do you can also specify the axis of the concatenation, so you can concatenate rows to rows or columns to columns. Welcome to another Numpy tutorial. In this tutorial, we're gonna see the arithmetic operations you can do using Numpy arrays. First of all, we want to import Numpy as MP. Then we specify 2 arrays, A and B, and try and add them. What you do is simply use the addition operation, and the result is an element-wise addition. You can also multiply 2 arrays by using a simple multiplication element by element. Please bear in mind that this multiplication will never be the multiplication that we see in linear algebra. You can also subtract an array from another array. Let's check it out. Exactly. The result is 0, 0, 0. You can also do a modulo operation, again, element by element. And you can also raise each element of an array A to the power of another array, for example B. In this case, as you can see, every element in B is raised into the power specified by A. Again, this is done element by element. Of course, you can do these operations with arrays of various sizes. For example, we have a 2.3 dimensional array here. So we can add A and B here. Again, when you multiply with the asterisk, what you do is not linear algebra multiplication. What you do is element-wise multiplication. And of course, there are a lot of other operations that you can do. For example, you can find the absolute value of an array. So if we put some minus values in the array A, actually use the function .abs from the Numpy library, we are gonna get the absolute value for each element of the array A. Of course, the result will be a new array with the absolute elements. You can also use a lot of other functions. I have specified some functions here, but you can also check out the documentation. Again, all of these functions are done element by element. In today's tutorial, we're gonna talk about linear algebra operations in Numpy. First of all, what you need to do is import Numpy as MP. Then we can use Numpy to do operations. For example, let's say that we want to create the identity matrix. We use numpy.identity and specify the rows and column values, and here you can see that we create a matrix with ones on the diagonal. And you can visualize the result by printing I. Then we can use a sub-library of Numpy that is called linalg that is specific for linear algebra functions. So for example, we can find the determinant of a matrix by using the linalg.det. Also, if we want to multiply 2 arrays, we can use the Numpy matmul that is specifically defined to do matrix multiplication like linear algebra does. So we can use this function, specify the arrays that are gonna be multiplied, and we can see the result here. We can also compute the dot product between 2 vectors by using numpy.dot. Finally, we can do the outer and inner product of an operation by using the numpy.outer and numpy.inner. We can also compute eigenvalues and eigenvectors by using numpy linalg.ieg. And here we can see the eigenvalues and the eigenvectors of this array. We can also inverse an array by using the linalg.inv function, and we can see here the inverse array. You can do a lot of other things with Numpy, but this is a very basic tutorial for it. Tutorial we're gonna talk about reversing and flattening arrays. So let's specify an array X that's gonna be 3.4 dimensional array, and we can use the .x or .travel, turn this array from a 3.4 dimensions into a 1 dimension array, meaning a vector of 12 elements. Let's check it out. So the only difference between flatten and ravel is that ravel does not return a copy. What does that mean here? If we specify x.ravel equals to a2 and then go and manipulate a2, you can see that the element in x has changed because .travel returns the position of x array. So this is really important to know, because if you do that, you may manipulate your original array and not knowing that you do not work with a copy. So if you want to keep x unchanged, what you want to be doing is using x.flatten that returns a copy of this array into a new memory position. So by manipulating k1 here, as shown in this example, you do not change the values in x. So let's try it out. Boom, x has not changed. You can also do flipping and reversing of arrays by using the np.flip. So what we can see here is that the array is flipped upside down through the diagonal. You can also specify the flipping operation. You can flip only rows, or you can flip only columns. Finally, you can use the numpy.sort to do sorting of arrays. So you can use numpy.sort and you can have your array sorted. So let's check it out. Boom, your array is sorted here. But bear in mind that np.sort is not an in-place operation. What it does, it returns a copy to a new sorted array. However, array.sort does in-place sorting of the array. So the original array is gonna end up sorted in memory. So just keep this in mind when doing sorting. Welcome to another Numpy video. In today's video, we're gonna talk about reshaping, transposing, and getting unique values and counts, and also broadcasting. First of all, let's specify an array that is gonna be having dimensions of 2.4, meaning 2 rows and 4 columns. You can use the .reshape function to change the shape of the array. So you can specify that you want the rows to be 4 and the columns to be 2. And Numpy is going to be reshaping your array according to your needs. So here you can see that the first row was split into 2 rows of 2 elements, and the same happened for the second row that became actual 2 new rows. Then you can use the .transpose or .t to transpose the array. Check out the result. What we can see here is that the array, the original one at least, becomes transposed. So the rows would become columns and the columns would become rows. And you can see the result here. So 1.2.3.4 was a row and now it became a column, while 4.5.6.8 was another row and became a column. And we can see the result here and here. .t and .transpose actually do the same operation. Moving on to the unique values and counts, we specify an array A and we use numpy.unique to find the unique values of array A. And we can see that the unique values will be 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And what it does, it actually returns the set. Its value in the set is going to be unique. So we see in the original array we have 2 12s, but here we only have 1. We can also use numpy.unique and also specify the attribute return index equals true, and you can get a tuple of results. The first one will be the unique values and the second one will be the first index where this value was encountered in. So for example, 11 was on the index 0, 12 was on the index 2, 13 was first encountered at index 3. And you can also return the counts of occurrence for its unique value, which is really helpful. So you specify attribute return counts equals true, and boom, you can see the count for its unique value in the original array A. Moving on to broadcasting, if you have a matrix and a number or a vector or something else, Numpy can understand that the multiplication should happen with each cell. So, if at least one of the dimensions is equal to 1 for either one of the two things you want to multiply, Numpy can understand and do cell-by-cell multiplication. If not even one dimension is compatible, it will throw a value error. So here, what Numpy does is that it broadcasts this array, this value, to each of the cells. So this is a 1.2 shaped array, and Numpy can actually do the multiplication by a number. And also here we can see two rows, and again it can multiply them because one of the dimension at least matches. So that's broadcasting. Okay, today we're gonna talk about computing statistics using Numpy. First of all, what you want to do is import Numpy as MP. Then what you wanna be doing is specifying a vector or an array. So first, let's specify A to be a Numpy array that is gonna be actually a vector of values 1.2.3. And we can find the minimum value of this array by using the .min function. So we can see that the minimum value of A is 1. Then we can find the mean value of A by using the .min function. And what we can see here is that the .min is 2.0. Finally, we can specify an array and compute the mean of the whole array, of the whole matrix. We can also do the minimum value and the minimum value per column and per row by specifying the axis attribute. Axis equals to 0 means the minimum value for each column. Axis equals to 1 specifies the minimum value per row. So if you visualize your array, what you can see here is that here we've got 2 rows and 2 columns. So by specifying min axis equals to 0, you can see that 2 and 3 are the minimum values for each column. Then you can compute the mean value per column and row respectively. What you can see here is that the mean value for each column is 3 and 4, while for each row it's 2.5 and 4.5. You can also find the maximum value again using the same thing. And you can also find the index, the position of the minimum, by using the arg.min function. If you specify no axis, each of these functions is gonna look on the whole matrix. Whereas if you specify the axis, it's gonna be by column or by row. And we can see here that the index position of the minimum value is the upper left. It's the 0 position. It's the value of 2. While the minimum argument per column is on the 0 index, which means the first row. While for each row, it is the first element. So finally, you can use .std to compute the standard deviation of the whole array, and again, you can specify the std per column or the std per row by using the axis attributes. Boom, you are good to go. Hope this helped you quite a lot. Welcome guys back to another Numpy tutorial. Today we're gonna talk about generating random numbers using Numpy. First of all, you can generate uniformly from 0 to 1 by using numpy.random.rand and specifying the size of the resulting matrix or the dimensions that you want to generate values from. So we can see here by specifying 3.3, you want a matrix of dimensions 3.3, meaning 3 rows and 3 columns. And we can see that each position, each cell in this matrix has values from 0 to 1. And these values are generated uniform at random. You can also do uniform generation of integer values within a range. For example, you can use numpy.random.rand int, that stands for random integer. you specify the upper bound and the lower bound. So the lower bound will be 0 and the upper bound will be 10, and 10 is not going to be included into the generation. And also you specify the shape of the resulting array. If you run this command, you can see that the values are quite random and they're from 0 to 9, setting a default random generator. You can use np.random.default.rng and sample from it. And this is the newer actual method of doing random generations. So you can do rng.integers and again specifying the range of values and the resulting shape. And this is the same with numpy.rand int. So if you run this code, you can see a different result, but it looks like uniform generation. And you can do also endpoint equals true attribute to include 10 into the values that are going to be generated. So if we run this code a couple of times, we can find 10 being inside the matrix. You can also do rng.uniform that will generate 3 float numbers between 0.10, and 10 is not included. If you want to include 10, you use endpoint equals true, and we can see 3 values from this range. Let's do it again. Boom. And each time you're going to be using this code, the values that are going to be generated, it's going to be different than before. If you do not set a random seed, then you can use the rng.random. This will generate 3 float numbers from 0 to 1, 1 not included. And boom, you can see 3 values here. And finally, you can use the standard normal to generate float numbers from a standard normal distribution with mean equals to 0 and standard deviation of 1. In today's tutorial, we're gonna learn how to save and load the NumPy array. First of all, we wanna be importing NumPy as MP, and then we wanna be creating 2 NumPy arrays. For the first array, we're gonna take values from 0 to 4, and the second array will be just the first one, the x in power of 2. So we can also print those arrays, and you can see here we have the first one from the values from 0 to 4, and the second one is the power of the first array. In order to save an NumPy array, what we want to do is use the save as function. The object we're going to be saving will be a .numpyz. If you use save as, what you are going to be doing is that you are saving these arrays as zipped arrays to a file. And you can also hover over the function to see a lot more information through the documentation. You can also specify a lot of other things here. So if we want to load this array, what we're gonna be using will be the np.load function. We will be specifying the name of the array and the file extension. Saved zipped arrays x and y are gonna be loaded into an array that has an attribute of files. And as we can see here, we have the x-axis and the y-axis because when we saved the array, we specified that we want x to be represented as the x-axis object and the y-axis object is going to be represented with y. So you can think of this like saving a dictionary NumPy arrays. So here how we are going to be accessing x and y is that we are going to be using the dictionary notation and we are going to be using the x-axis key and the y-axis key for x and y respectively. And as you can see here, we have recovered the X array and the Y array. There are also a lot of other ways that you can save a file using NumPy. You can, for example, use the numpy.save.txt. So we usually use this to save CSV files or text files. Again, you can hover over the function. You can see the attributes. So first of all, we want to be specifying the file name. Then we are gonna be specifying the array that we want to save. In our case, it is called array out. And we build it right here, and then we can specify the headers and also how the values are gonna be separated, which is actually the delimiter. For CSV files, it's the comma by default. You also see the attribute of header, which is a string, and this is gonna be the first line of the file, essentially. And you can also specify a footer, which will be the last line of the file. And also, if you want to load this CSV file or the text file, you can use load.txt, specify the name, the delimiters, and boom, you've recovered your saved array. Finally, you can use numpy.save function, which creates a .numpy_y object, which creates a numpy_y file. And you can also use numpy.load again to load the file name.npy by specifying the name and the extension of the file. All of this stuff are pretty basic. You have a lot of options according to what file you want to save and what file you want to recover. So the nb.save saves a binary file in NumPy. The np.load is used to load arrays or pickled objects from numpy and numpy or pickle files. Pickle file is another type of file that is used to save object, but this is outside the scope of this tutorial.